an unexpected gift to German intelligence. North Africa, November 1942. As Operation Torch unfolded across the Mediterranean coastline, American forces brought with them a weapon that would soon become their adversaries' most effective infantry anti-tank tool. The M1 Bazooka had arrived in theater without proper training protocols, a logistical oversight that General Dwight Eisenhower discovered the evening before the landings commenced. His soldiers possessed these revolutionary rocket launchers, but lacked any instruction in their operation. This training deficit would prove costly in ways the Americans couldn't anticipate. During the initial combat encounters, inexperienced U.S. units abandoned equipment when overwhelmed by German counterattacks. Among the discarded material were several pristine bazooka specimens, complete and functional. Wehrmacht technical intelligence officers recognized their significance immediately upon recovery. Revolutionary implications. The captured weapon systems represented a paradigm shift in infantry capabilities. Traditional anti-tank doctrine required specialized crews with heavy equipment, wheeled guns, or vehicle-mounted weapons that limited mobility and tactical flexibility. The bazooka changed everything. Here stood a device weighing merely 7 kilograms that 2 infantrymen could carry and operate, engaging armored vehicles at distances impossible for hand-delivered explosives. Wehrmacht analysts understood the strategic ramifications instantly. If American industry could equip every rifle company with portable anti-tank capability, German armor supremacy faced a fundamental challenge. Each infantry squad might soon possess tank-killing potential independent of artillery support or specialized units. Journey to Kummersdorf. German command expedited the captured weapons to the Reich for comprehensive evaluation. The specimens arrived at Kummersdorf Proving Grounds, located south of Berlin, where Wehrmacht weapons specialists maintained extensive testing facilities. This installation would become ground zero for understanding American rocket launcher technology and developing Germany's response. The technical examination proceeded systematically. Specialists disassembled each component, analyzed metallurgy, studied the electrical ignition mechanism, and tested the shape charge warhead against armor plate. The American design revealed both innovative thinking and critical vulnerabilities that German engineering could exploit. Technical assessment. The M1 launched 60mm rockets using battery-powered electrical ignition, a sophisticated approach that worked reliably in temperate conditions. The shape charge warhead could defeat approximately 75 to 100 millimeters of armor plate under optimal circumstances. Operation required minimal training, and the weapon's lightweight made it highly portable across varied terrain. However, German engineers immediately identified several design weaknesses that battlefield conditions would expose. The battery ignition system presented the gravest concern. Eastern Front experience had demonstrated catastrophically that batteries failed in extreme cold. The American bazooka's wooden shoulder stock contained 4 D-cell batteries, 2 active, 2 spare, but moisture penetration and freezing temperatures rendered them unreliable. Any German adaptation would require alternative ignition technology. The 60mm warhead size posed another limitation. Soviet T-34 tanks featured sloped armor that could deflect smaller shaped charges. German forces needed greater penetration capability to counter the armor they faced most frequently. Fortunately, Wehrmacht ordnance already produced 88mm shape charge warheads for the Raketen Panzerbuks 43 Pupschen, a wheeled anti-tank rocket launcher costing 5,730 Reichsmarks per unit. Adapting this proven ammunition to a shoulder-fire tube would provide superior penetration while utilizing established manufacturing infrastructure. Demonstration and decision. March 1943 marked the pivotal demonstration at Kummersdorf. German military officials observed captured American bazookas fired alongside experimental Wehrmacht anti-tank weapons, including the Foss Patron. This practical evaluation convinced senior leadership that developing a German rocket launcher was essential for infantry anti-tank capability. The captured weapons validated the fundamental concept. German engineering would now refine that concept into a weapon system optimized for Wehrmacht tactical requirements and environmental conditions. The development timeline would prove remarkably compressed, driven by urgent battlefield necessity and German industrial efficiency. German engineering solutions. The development process moved forward with impressive speed. Engineers tackled the battery vulnerability by implementing a magneto ignition system. A spring-loaded rod struck a generator to create electrical current on demand. This eliminated cold weather failures while maintaining reliable ignition across all environmental conditions. The tube diameter expanded to 88 millimeters to accommodate existing Pupschen ammunition, providing nearly 50% greater warhead mass than the American original. This decision leveraged established production lines and gave German infantry superior armor penetration capability against both American and Soviet tanks. One critical design compromise emerged during testing. The German rocket motor continued burning approximately 2 meters beyond the launch tube, unlike the American rocket that consumed its propellant internally. This extended burn increased both range and velocity, but generated a massive backlast that posed serious hazards to operators. Early testing revealed that exhaust could cause severe burns and temporary blindness, earning the weapon its enduring nickname, Ofenrohr, stovepipe. Official designation and production planning. By July 1, 1943, German documentation officially listed the weapon as the 8.8 centimeters Raketen Panzerbuchs. The designation soon evolved to Raketen Panzerbuchs 43, commonly abbreviated as RPSB 43. Production preparations advanced simultaneously at multiple facilities across Germany, though mass manufacturing wouldn't commence until September. The production infrastructure mobilized with characteristic German thoroughness. 6 primary manufacturers received contracts: Enzinger Union in Wehrheim, Hazig in Muselwitz, Jabr, Schneider in Berlin, Jekyll and Fritten, Kronprinz in Solingen, and Skirm in Pirna. Each facility produced components or complete weapons, with final assembly distributed across multiple locations to prevent Allied bombing from crippling the entire program. Rapid deployment timeline. September 8, 1943. German military reports indicated the weapon would reach frontline troops for field trials imminently. By September 30th, the official operational manual for the Raketen Panzerbuchs had been published and distributed. October 5th witnessed the first delivery of 1,500 weapons and 5,000 rockets to combat units. The transformation from captured American weapon to German mass production had required less than 11 months. Production figures revealed the Wehrmacht's commitment to the program. Initial orders specified 382,000 units, though material shortages and strategic bombing reduced actual production to 289,151 RPSB 54 models by July 1944, when that variant ceased production. An improved RPSB 54/1 model entered production in December 1944, with 25,700 units manufactured before Germany's surrender. Economic efficiency. Manufacturing a Panzerschreck required merely 10 work hours per weapon at a cost of 70 Reichsmarks, compared to 5,730 Reichsmarks for the smallest conventional anti-tank gun. This economic efficiency enabled mass production even as Germany's war economy contracted under Allied pressure. A single Panzerschreck cost less than a military rifle, yet could destroy a 40-ton tank. The dark reality of production. The human cost of production constitutes one of the weapon's darkest chapters. Hazig, the third largest exploiter of forced labor in Nazi-controlled Europe, operated multiple production facilities using slave laborers from concentration camps. By October 1943, over 60,000 workers labored for Hazig, more than half forced laborers and prisoners of war. The company operated 165 prisoner labor subcamps by 1945. At Hazig facilities in Poland, approximately 35,000 deaths occurred across various camps, though incomplete records prevent precise accounting. Workers endured 12-hour shifts with exposure to toxic chemicals, brutal beatings, starvation rations, and absent sanitation. The Schlieffen camp, producing munitions including Panzerschreck components, housed between 2,000 to 5,000 female prisoners, with an average life expectancy of 2 months. An explosion on October 12, 1944, killed 96 prisoner laborers instantly. Initial combat deployment. Weapons deployment began in autumn 1943, initially in limited numbers as production scaled up. By January 1944, 21,141 Panzerschrecks had been issued to combat units, though another 39,526 remained in armories due to Wehrmacht distribution challenges. German infantry units across all fronts requested the weapon, recognizing its effectiveness against Allied armor. Eastern Front forces received priority distribution. Soviet tank commanders quickly noticed the tactical shift. Where German infantry previously relied on magnetic mines, anti-tank rifles, and bundled grenades, all requiring close approach to enemy armor, they now possessed weapons engaging tanks at 150 to 200 meters. Every German defensive position potentially concealed multiple rocket launcher teams. Tactical doctrine development. The weapon proved exceptionally effective in defensive positions. German tactical doctrine evolved to employ Panzerschreck teams in interlocking fields of fire from concealed positions. Teams occupied staggered trenches positioned no more than 150 meters apart, ensuring attacking armor faced rockets from multiple directions simultaneously. Effective range against moving targets approximated 100 meters, though static targets could be engaged at greater distances. Technical performance data from German and Finnish testing demonstrated impressive capabilities. The RPSB Grove 43-22 rocket achieved penetration of 160 mm armor at 60-degree impact angles, or up to 230 mm at optimal 90-degree angles. Rocket velocity reached 110 meters per second compared to the American Bazooka's 85 meters per second. The warhead contained 700 grams of explosive, triple the American weapon's charge. The Shield Edition. February 1944 brought the Blast Shield Edition, creating the RPSB 54 model that became the standard production variant. This shield protected operators from rocket backlast, though it increased weight from 9.25 kilograms to 11 kilograms. Operators still required protective equipment, including gloves and face protection, as the backblast danger zone extended 10 to 30 meters behind the weapon. Western Front employment. Western Front deployment accelerated before D-Day. German forces in Normandy received thousands of Panzerschrecks, positioned to engage Allied landing craft and tanks at waterline positions. The weapon proved highly effective in bocage country, where short engagement ranges and abundant concealment suited Panzerschreck tactics perfectly. American tank crews, recognizing their own invention turned against them, developed countermeasures including additional armor plating and infantry screening tactics. Despite these adaptations, the Panzerschreck remained a formidable threat. Psychological impact. The psychological effect often exceeded physical damage. Allied tank crews understood that every hedgerow, building, or rubble pile might conceal a Panzerschreck team. The weapon's distinctive launch signature, a bright flash followed by a smoke trail, became a dreaded sight on battlefields from Normandy to Berlin. Tank commanders reported that crew effectiveness decreased significantly in areas with known high concentrations of Panzerschrecks. International proliferation. International proliferation began before the war ended. Finland purchased 1,854 launchers and 18,650 rockets for 200,000 Reichsmarks. Finnish forces achieved remarkable success against Soviet armor, with testing confirming penetration of 100 mm face-hardened armor at 30-degree angles. Hungarian forces received Panzerschrecks for Operation Spring Awakening in March 1945, the war's final major German offensive. Allied intelligence response. Allied intelligence closely monitored the Panzerschreck phenomenon. A British report from January 1945 noted that German production of nearly 300,000 units in 18 months exceeded total Allied bazooka production for the same period. American ordnance experts acknowledged that Germans had identified and corrected every weakness in the original bazooka design, creating a superior weapon from captured examples. the Americans adopted German improvements for later bazooka models. The M1 Bazooka, introduced in October 1943, incorporated magneto ignition similar to the Panzerschreck, eliminating the battery problems plaguing earlier versions. The M20 Super Bazooka, developed late in the war, increased caliber to 3.5 inches, following the German example of using larger warheads for enhanced penetration. Production statistics and infrastructure. Production statistics reveal the weapon's importance to German strategy. By July 1944, when RP's B-54 production ceased, 289,151 units had been manufactured. Monthly production peaked at 15,000 units in early 1944. Each weapon required components from 32 subcontractors, demonstrating the industrial complexity behind mass production. The improved RP's B-54/1 model addressed remaining deficiencies. Introduced in December 1944, it featured shortened tube length of 135 centimeters, improved rocket propellant reducing backlast, and refined sights. Despite orders for 48,000 units, only 25,744 were delivered before Germany's surrender. Engineers also developed prototypes using impregnated cardboard tubes to conserve steel, though none reached production. Cost-effectiveness analysis. Cost-effectiveness analysis demonstrates why Germany prioritized Panzerschreck production. Each weapon cost 70 Reichsmarks and required 10 work hours to manufacture. The smallest traditional anti-tank gun, the 3.7 centimeters, Pak 35-36, cost 5,730 Reichsmarks and proved ineffective against modern tanks. A single Tiger tank cost 300,000 Reichsmarks. For one Tiger's price, Germany could produce over 4,000 Panzerschrecks. Ammunition production matched weapon manufacturing. Over 2 million rockets were produced, primarily the RP's B Grove 4322 model, with its distinctive shape and fin stabilization. Each rocket weighed 3.3 kilograms and came packaged in wooden crates of 2. Special winter and summer variants accommodated temperature extremes affecting propellant performance. Transport frames allowed soldiers to carry 5 rockets, though weight and bulk limited mobility. Post-war influence. The weapon's influence extended far beyond World War II. Belgian company Mekker, which had produced Panzerschrecks under license, developed the blindicide RL-83 in the 1950s using similar principles. The Swiss Army adopted derivatives as the 8.3 centimeters Raketen Rohwehr, maintaining upgraded versions in service through 1980. The fundamental concept of an oversized shaped charge in a shoulder-fired tube influenced anti-tank weapon development worldwide. Post-war analysis. Post-war analysis by American ordnance experts acknowledged German achievements. Colonel C.T. Richards wrote in 1946 that the Panzerschreck program represented history's most successful reverse engineering project, achieving mass production in under 7 months from initial captured specimens. The Germans had transformed a hastily developed American weapon into a mature system, exceeding the original in every performance metric. Soviet forces captured thousands of Panzerschrecks during their advance into Germany. Red Army evaluations noted the weapon's superiority to captured American bazookas received through Lend-Lease. The Soviets had initially rejected American bazookas as insufficiently powerful, receiving only 3,000 units with minimal ammunition. The German version, with its larger warhead and greater penetration, better suited Soviet tactical requirements. Extended service life. The last documented combat use of wartime Panzerschrecks occurred during the 1948 Arab-Israeli War, when Syrian forces employed captured German weapons. These weapons had traveled from German factories through various conflicts, demonstrating the durability of the basic design. Some examples remained in Third World arsenals into the 1960s, long after more advanced anti-tank weapons became available. Technical documentation. Technical documentation survived in remarkable detail. The Wehrmacht's September 30, 1943 manual provided comprehensive instructions for operation, maintenance, and tactics. American intelligence translated captured manuals, with an October 7, 1944 report detailing German firing procedures, aiming techniques, and safety requirements. These documents reveal the thoroughness of German training programs despite wartime pressures. Safety concerns. Safety statistics highlight the weapon's inherent dangers. German records indicate numerous operator casualties from backblast injuries, premature detonations, and enemy return fire attracted by the weapon's prominent launch signature. The 10 to 30 meter backblast zone behind the weapon required careful positioning to avoid injuring friendly troops. Urban combat proved particularly hazardous, as backblast could reflect off walls, injuring operators. Comparative analysis. Comparative analysis with contemporary weapons reveals the Panzerschreck's position in anti-tank weapon evolution. The British PIT, using a spring-launched spigot mortar principle, had greater range but less penetration. The American Bazooka offered better portability but inferior armor penetration. The German Panzerfaust provided simpler operation and lower cost, but was single-use only. The Panzerschreck balanced these factors, offering reusable capability with substantial hitting power. Manufacturing quality variations. Manufacturing quality varied significantly as the war progressed. Early production weapons from 1943 featured excellent workmanship with precision-machined components. By late 1944, simplified production techniques and inferior materials reduced quality, though functionality remained adequate. Captured examples show progressive degradation in finish and tolerances as Germany's industrial situation deteriorated. Complete infrastructure. The weapon system's complete infrastructure included training facilities, ammunition depots, repair workshops, and distribution networks. Germany established Panzerschreck training schools at multiple locations, graduating thousands of operators monthly. Specialized repair units maintained weapons at division level. The logistical commitment matched that of traditional artillery systems, demonstrating the weapon's perceived value. Environmental limitations. Environmental limitations affected combat employment. The weapon proved less effective in extreme cold, where propellant burned inconsistently. Desert conditions caused problems with sand contamination. Rain and moisture could cause electrical shorts in the ignition system. Despite these limitations, the basic design proved remarkably robust, functioning adequately across diverse combat environments, from Arctic Finland to Mediterranean Italy. Allied countermeasures. Allied countermeasures evolved throughout the war. Tank crews welded additional armor plates, hung sandbags, and installed wire mesh screens to defeat shaped charges. Infantry adopted aggressive screening tactics, advancing ahead of tanks to suppress Panzerschreck teams. Artillery and mortars targeted suspected firing positions. Despite these measures, the Panzerschreck remained a serious threat through the war's end. Tactical innovation. German tactical innovation maximized the weapon's effectiveness. Panzerschreck teams learned to target specific vehicle vulnerabilities, including vision blocks, engine compartments, and track assemblies. Multiple teams coordinated attacks to overwhelm tank defenses. Urban combat tactics evolved to exploit the weapon's capabilities while minimizing exposure to return fire. These tactics influenced post-war anti-tank doctrine worldwide. Quality control and production challenges. Production quality control data survives from several facilities. Random testing of production weapons showed approximately 95% met specifications in 1943. Declining to roughly 80% by late 1944. Primary failures involved ignition systems and tube integrity. Despite quality issues, sheer production volume ensured adequate supplies reached combat units. Economic impact. The economic impact extended beyond direct production costs. Germany diverted significant industrial capacity to Panzerschreck manufacturing, including steel, electrical components, and chemical production for propellants and explosives. The program consumed resources that might have produced other weapons. However, cost-effectiveness compared to traditional anti-tank guns justified this allocation. Evolution of training. From the German perspective, training programs evolved based on combat experience. Initial training emphasized accuracy and safety. Combat veterans later provided practical instruction on tactics, camouflage, and survival. The Wehrmacht published numerous training pamphlets and tactical guides specifically for Panzerschreck operators. These materials, captured and translated by Allied intelligence, provide insights into German anti-tank doctrine evolution. Supply chain complexity. Supply chain complexity increased as production expanded. The weapon required specialized components from multiple suppliers, including electrical contacts, optical sights, steel tubing, and wooden components. Rocket production demanded separate facilities for warhead manufacture, propellant mixing, and final assembly. Disruption at any point could halt production, making the system vulnerable to strategic bombing. Demonstration of rapid adaptation. The Panzerschreck program ultimately demonstrates rapid military adaptation under extreme pressure. From initial capture of American bazookas in November 1942 to mass production by September 1943, Germany transformed a foreign concept into indigenous capability. The program succeeded through pragmatic engineering that adapted existing resources rather than developing entirely new technology. Germany's ability to produce nearly 300,000 Panzerschrecks while fighting a multi-front war reveals remarkable industrial resilience. The weapon emerged from systematic reverse engineering that identified and corrected original design weaknesses. German engineers didn't simply copy the bazooka. They created a substantially improved weapon system that exceeded the original in every measurable performance criterion. Historical significance. The historical significance extends beyond technical achievement. The Panzerschreck represents successful technology transfer under combat conditions, rapid industrial mobilization despite resource constraints, and effective military adaptation to enemy innovations. The program proved that captured enemy technology could be quickly transformed into mass-produced weapons that influenced battlefield outcomes. Modern military historians study the Panzerschreck as a case study in successful reverse engineering, rapid product development under wartime conditions, and industrial mobilization. The timeline from capture to mass production remains impressive even by modern standards. Few weapons programs have achieved similar speed from concept to deployment, particularly when starting from captured enemy equipment. The complete picture. The complete story encompasses technical innovation, industrial achievement, and human tragedy. While German engineering deserves recognition for rapid development and successful mass production, the extensive use of slave labor cannot be ignored. Tens of thousands died producing weapons that extended a lost war. The Panzerschreck's history includes both remarkable technical achievement and systematic exploitation of forced laborers. Lessons for military history. The Panzerschreck stands as history's most successful reverse engineering program, transforming captured American bazookas into nearly 300,000 improved German weapons in under 1 year. The program demonstrated that military innovation could be borrowed, improved, and mass-produced faster than previously imagined. From the first captures during Operation Torch to the final weapons produced in April 1945, the Panzerschreck represented German industrial capability and engineering pragmatism applied to desperate military necessity. The weapon's legacy influenced anti-tank weapon development for decades, with its fundamental design principles still evident in modern systems. Final assessment. The success of the Panzerschreck program can be measured across multiple dimensions. Technically, it exceeded the American original in penetration, range, and reliability. Economically, it provided cost-effective anti-tank capability compared to traditional guns. Tactically, it empowered infantry units with organic anti-tank capability independent of specialized support. However, this success came at tremendous human cost through the exploitation of slave labor in production facilities. The weapon story serves as a reminder that technological achievement cannot be separated from the ethical context of its creation. The Panzerschreck remains a significant weapon in military history, not just for its technical merits or combat effectiveness, but as an example of how rapidly military technology can be adapted, improved, and deployed when national survival appears at stake. Its development timeline continues to inform modern discussions about military procurement, reverse engineering, and rapid capability development. The weapon's influence persists in modern anti-tank systems that still employ variations of the shape-charged warhead in a portable tube concept that the Panzerschreck helped perfect through systematic engineering improvement of captured American technology.